Okay, so I'll take just 10 more minutes and then we can close today's session. It's regarding NMR, ESR, electron spin resonance spectroscopy. That is what is ESR. We saw nuclear spin resonance. This is electron spin resonance. So nuclear spin resonance was related to energy being absorbed by the nucleus. Electron spin resonance is the energy being absorbed by the particular electron. Now, one major difference, both of them will behave or will have the same basic operating principle, that there is a magnetic field in which that electron or nucleus will spin and precess. We have to find out a resonance condition for them. In the case of a nucleus, the resonance condition occurs when you apply a radio frequency signal, because the energy required to resonate a nucleus is in the range of radio frequency. Whereas for an electron, the energy will be in the range of microwaves, that is in gigahertz. That is the basic difference between NMR and ESR. Both of them will study a particular sample, actually the chemical condition of a particular sample. But the difference is in having either your NMR or ESR. So NMR will have radio frequency signal required to resonate the nucleus. In an ESR, you will require a microwave signal to resonate the particular electron. Okay, so here it is written, it is the study of magnetic dipoles of electronic origin by applying usually a fixed microwave frequencies to a sample placed in a varying magnetic field. It is also called as electron paramagnetic resonance spectroscopy. Its areas of application are chemistry, physics, biology, and medicine. It is used to study molecular structure, reaction kinematics, molecular motion, crystal structure, electron transport, and relaxation properties of an electron. It operates in the same way. As I said, the magnetic moment here is called a Bohr magneton. Only odd number of electrons exhibit characteristics of magnetic properties. Even number of electrons will not exhibit such properties. That means you require an unpaired electron to do it. Working principle is similar to that of NMR, except that in this case, the sample has to be irradiated with a microwave frequency rather than a radio wave frequency. Why? The simple reason being, electron has smaller mass and a larger magnetic moment than a proton, which is there inside a nucleus. So for a given magnetic field, the precession frequency is therefore higher as compared to a particular nucleus. That is the simple reason to understand why we require microwave rather than requiring a radio frequency signal. Are you able to see the presentation now? I did not share it a few moments back. So basically we'll be considering the electron only. In this situation, the electron has a smaller mass and a larger magnetic moment. Hence, it will require a larger frequency to precess. So we require microwaves instead of the radio waves which are used in NMR. This is the basic block diagram of ESR. In this, the system remains the same. You have a magnetic cavity. You have a magnetic cavity in which you are placing the sample. Okay. Here is something called as the klystron. This klystron is nothing but a microwave generator. That will be explained later on. And then you have the same system. You have a system to detect the microwaves which are emitted from the sample and then displayed on the meter. See, this is a klystron. Okay, it gives an energy between 10 to 500 megawatts. Frequency range is 1000 to 25,000 megahertz. And it basically has a heated cathode, a filament. Okay, there's an electron pathway, there's an anode, and there's a reflector electrode. So from the electron, basically, so there are three electrodes, a heated cathode from which electrons are emitted, an anode to collect the electrons, and a highly negative reflector electrode which sends these electrons which pass through a hole in the anode back to the in the anode back to the anode, means on the opposite side of the anode. The motion of the charged electrons from the hole in the anode to the reflector and back to the anode generates an oscillating electric field and thus an electromagnetic radiation which will be in the range of microwaves. Thus, the microwave frequency can be tuned or adjusted over a small range by adjusting the physical distance between the anode and the reflector, which is very difficult to alter. So there's a very small range in which you can adjust this. In practice, both methods are used. The metal tube is distorted mechanically to adjust the distance, and the reflector voltage is adjusted as a fine control. I hope it has helped you all, and I am going to have another session for the next topic. Now this has completed our module number 3, and for the next session, that is atomic absorption spectroscopy and atomic emission spectroscopy. I've already put up the presentation on the website. Please go through it, and I will schedule the lecture maybe tomorrow. And Bipin, your query that whole of the anode and back to the anode is basically it is being reflected. If you observe the diagram, there is a small hole. There's a pathway provided for the anode or for the electrons to flow towards the reflector, and from the reflector it will come back. It will come back, and there will be a pathway for it to pass to the anode on the other side. So if this is the anode, it will pass here, go here, reflect, and come back. That is what it is doing. So in actually passing this way, it is oscillating, or it is creating an oscillating field, oscillating electric field, which is nothing but your electromagnetic radiation. Thank you everyone for attending, and see you tomorrow.